Yesterday we learned about a few of the trends for the periodic table, and the big one is the atomic size, the radius. Just to remind you, we learned that the atomic radius is the biggest in the bottom left corner of the periodic table, and it's the smallest in the top right corner. So atoms tend to get bigger as you move towards the left, and they get bigger as you move down. Today we're going to learn about electronegativity. So first go ahead and write down that definition. Electronegativity is the ability of an atom to attract electrons when the atom is in a compound. And this word is actually going to be really important in our bonding unit because we're going to talk about how atoms share electrons, but they don't necessarily share them equally because some of them pull more than others. So electronegativity is the ability to pull those electrons toward it. So if you picture a really, really big atom versus a really, really small atom, the small atom is going to have more pull because the electron can just stick right onto that little nucleus. It's right next to the nucleus of the atom. Whereas if you have a really big atom, the electron that's sticking on is so far away from the nucleus that it really can't feel that positive charge very well, and so it doesn't stick on as well. So what that means is that electronegativity is going to increase towards the smaller atoms. So as you go from bottom to top, the electronegativity is going to increase. And the reason is because at the top of the periodic table you just have a few energy levels, whereas at the bottom you have a ton of energy levels. And again, energy levels are those rings around the nucleus. So at the bottom, because they have so many energy levels, the attraction between the positive nucleus and that outer little electron is very weak because all that stuff is in between, and the fancy word for talking about all that stuff is the shielding effect. We used the analogy last week that a refrigerator, if you put a whole bunch of papers on a refrigerator and try to stick a magnet on it, the magnet can't really feel the pull of the refrigerator because there's so much stuff in between. It's the same idea here. So that little electron, if it's trying to stick onto a really big atom, it really can't feel that pull very much, so it has a low electronegativity. Whereas at the top of the periodic table, since there's just a few energy levels, it can really feel that pull, so it's a higher electronegativity. From left to right, remember we talked about that you add protons, and so the more protons you have, the more likely the electron is to be attracted to that nucleus. So in general, it increases as you go left to right. And the reason is because of that nuclear charge, which is just a fancy way to say you have more protons. But notice that fluorine is the most electronegative, not helium. Helium is in the very top right. And the reason is because you have to ignore the noble gases for this trend, and that's because noble gases are already stable. They already have a full valence octet, so no matter what kind of size they are, they're never going to attract electrons because they're already completely stable. So the trend is that it's going to increase up and increase to the right, but in this case you stop at the noble gases. So this is what it looks like, but again you're going to stop at that last row. It doesn't go all the way to the edge of the periodic table. So next to your definition of electronegativity, just draw an up arrow and a to the right arrow. So take a minute and pause this video and see if you can figure out which of these elements has a greater electronegativity, and then check your answers. For the first one, you should have gotten chlorine because it's higher up on the periodic table, which means it has fewer valence electrons. So that electron is going to be more attracted to that smaller atom. Phosphorus versus magnesium. Phosphorus is farther to the right, which means it has more protons. So the electron is going to be more attracted to it. And of the last one, it's tempting to say neon because it's the farthest up and to the right, but remember noble gases have a very low electronegativity because they're already stable, so we're going to go with phosphorus for number 3 as well. And the last trend is actually different from metals versus nonmetals. So first we have to review the difference between them. Metals, their entire job, everything that they're trying to do is to lose electrons. So anytime you put them with other elements or try to do a reaction, metals are always going to try to give away their electrons. And the reason is because they only have a few valence electrons. So if you look at that periodic table, everything to the left of the staircase has either 1, 2, or 3 valence electrons. So it's a whole lot easier for them to just get rid of those few and then they're stable than it is to try to gain a whole bunch of electrons to fill up that outer shell. And since metals are trying to lose electrons, we talked about earlier that it's easier to lose them if the atom is really big, because you have that shielding effect, and the electron is just so far away from the nucleus it practically just falls right off. So when you think of metals, think of losing electrons, and it's easier to do that if it's big. Nonmetals are the opposite. Nonmetals are always trying to gain electrons, and that's because they already have a lot. Nonmetals have like 5, 6, or 7 valence electrons, so it's easier for them to just gain a couple to get that magic number of 8 than it is to try to lose 5, 6, or 7. And when you're gaining electrons, it's easier to gain them if the atom is small, because the electron's just going to stick right onto that positive nucleus. So nonmetals are more reactive if they're small. But keep in mind, we're excluding the noble gases here as well, because they're not reactive at all. They're already stable. So notice these two trends. For metals versus nonmetals, notice how it's split down the middle with the staircase. Nonmetals go towards the top right corner, but don't forget that it stops at the noble gases, so this column is actually not there. Metals go towards that bottom left corner. So for metal reactivity, or if I say the most metallic elements, are going to be the largest ones. And that's because they're so big that they can lose that little electron really easily. So the most reactive metal is going to be francium in that bottom left corner. For the nonmetals, the smallest atoms are the most reactive for nonmetals, so they're going to be towards the top right corner. They're complete opposite directions. Don't forget to exclude noble gases. So the most reactive nonmetal is not helium, it's actually fluorine. So what I tell students is just to remember that the most reactive elements are francium and fluorine, the two Fs. And the trends are going to go towards those Fs. So as you get closer to fluorine, if you're a nonmetal, it's more reactive. As you get closer to francium, it's more reactive. And the last thing is just a summary of all the trends that we learned. So we talked about how atomic radius gets bigger to the left and down. That's this first one right here. We also talked about yesterday ionization energy, which goes to the right and up. And then today we learned electronegativity, which is the same as ionization energy. The only difference is that it doesn't go all the way to the noble gases. And the last two are the red and green ones. Those are the metal and nonmetal reactivities. So they're split on the staircase and they go towards opposite directions. So just remember that 2 trends go left and down, and 3 go to the right and up. And you will need to memorize these trends, or at least be able to draw them on your test to make sure that you understand the trends. And the 2 that you should put a star by are the electronegativity and the non-metallic properties. Those are the 2 that go to the right, but they don't go all the way to the noble gases. They stop before the noble gases. So again, put a star by electronegativity and non-metal reactivity. And that's it for this chapter. So there's really 2 sections. There's all the different families, metals versus nonmetals, all that kind of stuff. And then there's the trends. Those are the things that you'll be required to know for your test. Thanks a lot.